Our first speaker is Ilya Mandel, who's a professor of theoretical astrophysics at Birmingham. Ilya is going to talk to us about studying black holes and gravitational waves and why uncertainty quantification might be helpful in what he does. But really, in many ways, this is a challenge problem. This is an opportunity for us to see another field who's not a PDE person necessarily and not a statistician necessarily, and see that there's room for collaboration. And so one of the things that I hope that would come out of this is that maybe Ilya will walk away with a whole bunch of collaborators who will solve all of his problems. So without further ado, Ilya.
Thank you. Let me see if I can figure out how to attach this. 1 moment. Hi. Thank you very much for the introduction, Derek. So, as Derek said, I am neither a PDE person nor a statistician. I do some astrostatistics, but mostly I'm here to come to you with a plea for help. So I come from a field which is very rapidly developing, is getting lots of exciting results, but also has lots of challenges that I hope some of you can maybe help us address. So the field is gravitational wave astrophysics, and let me just very briefly lay out what this field is, what we're talking about, why the problems are relevant, and then I'll get on with the problems themselves. So some of you may remember this picture, and probably when George Lucas was drawing the two suns over the planet Tatooine, he figured that this was a nice science fiction kind of thing. It's actually not science fiction. It's the typical reality. It's us who are weird. Most stars in the universe come in binaries. They come with companions. Some of them actually come in more than binaries. Some of them come in triples and quadruples and so on, but for interests of propriety, we won't discuss those. So let's talk about the ones in binaries. So, and especially massive stars, heavy stars, stars much heavier than our sun, stars that are 10 or 20 or 30 or 40 times the mass of our sun, they almost always come in binaries, frequently with a comparable mass companion. Now, sometimes those stars are so far apart that they don't interact. Sometimes the binaries are closer, and the stars will actually interact with each other. So here is a picture of two stars where one star has expanded enough that the tidal field of the other star is now pulling on it and grabbing some of the material from the companion, and there's mass transfer going on between the stars. There are various kinds of interaction through tides, interaction through actual mass transfer, of course, interaction through gravity. That's what makes the two stars in a binary go around each other. There are also other things that can happen to these massive stars. They lose mass through winds. They explode in supernova explosions, leaving behind very dense, very compact objects, neutron stars and black holes. And there can be a whole history to these interactions. So here's a possible sketch for how you might make two black holes. You start out with two stars, there is some mass transfer, there's a supernova explosion, some wind mass loss, maybe something very mysterious called the common envelope phase that I won't bore you with. And in the end, actually this is the one place where we don't have too many question marks. You end up with, although possibly we should, you end up with two black holes, and when you have two black holes orbiting around each other, they emit something called gravitational waves. So gravitational waves are ripples in space-time. They are features of the space-time itself. They were prescribed or described by Einstein very shortly after the formulation of the general theory of relativity. GR came about in 1915. By 1916, Einstein had already written his first paper on gravitational waves. Turns out it was a bit wrong. By 1918, he fixed the mistakes, and there was already this idea that, in general, if you have two objects orbiting around each other, or for that matter, even a single object that's not axisymmetric, that's rapidly rotating, you end up creating these disturbances in space-time, kind of like ripples on the surface of a pond after you drop a stone into a pond, that move outwards with the speed of light and that stretch and squeeze space in directions perpendicular to the direction of propagation. So, in other words, if you want to think of a gravitational wave, think of trying to maybe impress a potential partner, right? You want to maybe look very tall and very thin for the sake of this partner, so just ask them to look at you in exactly the right phase of the gravitational wave. When a gravitational wave passes through, it's going to stretch you this way and squeeze you this way. Now, just before you do this, two pieces of warning. One is make sure the partner looks during the right phase, because of course in the next phase you will be stretched this way and squeezed this way, so maybe a little less impressive. Secondly, make sure your partner has excellent eyesight, because for the typical gravitational waves we see here on Earth, that stretching and squeezing will be by about 1 part in 10 to the 21st power. That is why Einstein himself concluded that gravitational waves, exciting as they are not really going to be something that is going to be detectable in any realistic setting. Because he figured that, yes, if you were sitting right there next to two black holes, of course, the gravitational waves can actually be very strong and very luminous. In fact, during a merger of two black holes of equal mass somewhere in the universe, the peak luminosity, meaning the peak energy per unit time that is removed in gravitational waves, exceeds the combined light of all of the stars in the visible universe. So these are very, very bright events that carry away a lot of energy, because there's a lot of gravitational energy in this pair of black holes moving around. And ultimately, as the gravitational waves carry away the energy, that's what makes the binary spiral in and come closer together over time as energy is removed. But we live far away from any pairs of merging black holes, and of course gravitational waves, their strength decreases as 1 over r, where r is the distance to the source. That's true for any wave, electromagnetic wave or gravitational wave. And so we don't necessarily expect these things to be detectable. But nonetheless, let's say for the sake of curiosity, let's actually hear what a gravitational wave sounds like. And I say here, I should be a little bit careful. Of course, gravitational waves are stretching and squeezing of space. It's not a vacuum. It's not something you're likely to hear with your ears. But because the vacuum is because the space is being stretched and squeezed in a way that, at least for some of the sources that I mentioned today, are actually in the audible frequency band, we're talking between tens and thousands of hertz, it makes more sense to listen to them than to look at them, perhaps. So let's try this. So that, you just heard a gravitational wave from a 1.4 solar mass neutron star spiraling into a 10 solar mass black hole. Now this animation made by one of my students at Birmingham actually doesn't muck around with anything except for the amplitude, right? So the frequency is really the frequency. The rate at which the frequency is evolving is the real rate at which the frequency will be evolving during the last few seconds during the merger of these objects. So you hear this characteristic chirp, and you can see this on this plot over here. This is just a zoomed-in version of the late phases of it, which shows you that two things are happening. First, the amplitude is increasing, and secondly, you can see here the frequency is increasing with time, right? So that's simply because as the two black holes, or the neutron star and the black hole, or two neutron stars, are moving around each other, as they spiral in, of course, the frequency is higher here, the period is shorter, and the gravitational wave frequency just tracks the Keplerian orbital frequency. And secondly, the interaction gets stronger and stronger, so the amplitude gets higher and higher. And so that's why you're seeing this characteristic chirp. Now, that was a chirp from a 1.4 solar mass neutron star falling into or spiraling into a 10 solar mass black hole. Let's consider, just as an alternative, two more massive objects. In this case, this is going to be a 14 solar mass and a 50 solar mass black hole, just randomly chosen numbers. So you still hear this characteristic chirp, this characteristic increase in frequency and amplitude, but you also hear that there's some difference, right? The rate at which the frequency was changing is a little bit different. The final peak frequency was a little bit different. It was lower in this case when the objects are more massive, right? These subtle differences tell you that, okay, there's hope. There's hope for both for detecting these things, because if you build an instrument sensitive enough, because there is a somewhat generic picture here, right? A generic kind of chirp you can search for. But there's also hope to learn about the properties of the individual events, because there are subtle differences between the signatures of two merging black holes depending on their masses and depending, as it turns out, on other parameters such as their spins, their sense of rotation around their own axis, for example. And that tells you that ultimately you might hope that if you do get a signal, you can go back and do inference on it and figure out what were the actual properties of the two objects spiraling into each other. Now, why is this timely? Well, okay, one of the obvious reasons why it's timely is because of this. So last autumn, the a triumvirate of three fantastic physicists, Barry Barish, Kip Thorne, actually my PhD advisor, and Ray Weiss, got the Nobel Prize in Physics for the discovery of gravitational waves. Now, gravitational waves weren't technically discovered by them. They are extremely clever guys, but as you can see, they're all getting a little bit on in the air, so they certainly don't have the eyesight to see these changes of 1 part in 10 to the 21st. They were discovered by this instrument, which of course they were played an instrumental role in getting off the ground, but it's actually a huge collaboration, something like 1,000 people that are behind us now. And this is called the LIGO instrument, Laser Interferometer Gravitational Wave Observatory. So this is what it looks like. This is one of the LIGO sites. This one is located in Hanford in Washington State. There's another one just like this, but a lot more green, located in Louisiana. And then there's a shorter one in Italy called Virgo. And there are a couple of other instruments still being planned in development in Japan and in India. And the basic picture is something like the following. You have laser light that comes in, gets split by a beam splitter, goes out the two arms. At the ends of the two arms of this 4-kilometer interferometer, there are test masses that are basically mirrors on freely swinging pendula. When a gravitational wave passes through, it stretches one arm and squeezes the other arm, making the interferometer look like this. Okay, this is a somewhat exaggerated picture, but basically this arm, let's say, swings out, this one comes in. When the light comes back after being reflected off of these mirrors, it's now out of phase, and you can see the phase difference between the length of the two arms through this detector here. And you might say, well, is this actually realistic? Because after all, okay, this thing is, let's say, a few kilometers, right? So for round count, let's say 10,000 meters. I told you that the typical stretching and squeezing is at the level of 10 to the minus 21, right? That's a fractional stretching and squeezing, right? So that's, if it's a 10-kilometer thing, that means you're stretching it by 10 to the minus 21 of the 10 kilometers. So we're talking about 10 to the minus 17 meters. Okay, now, most of you I know don't come from physics, but just to give you a sense of scale, okay, the wavelength of light, we're talking about, let's say, visible light, 500 nanometers. So 5 times 10 to the minus 7 meters. If we're talking about the size of a hydrogen atom, we're talking about 10 to the minus 10 meters. If we're talking about the size of the nucleus, we're talking about 10 to the minus 14 meters. And you want to measure these mirrors, which are blobs like this, they're several tens of kilograms in mass. You want to measure their position to 10 to the minus 17 meters, 1/1000th of the size of the nucleus. Good luck. Well, I say good luck, and Einstein clearly thought good luck, but after about 30 years of hard work, the experimentalists have actually managed to do it. So this is an amazing thing. This is the sensitivity of the instrument, and there are all kinds of sources of noise, from the ground shaking because you and I are moving along, to thermal noise on the mirrors because the mirror surfaces fluctuate like this, Brownian motion of the atoms, to shot noise because you're actually getting to, even though you're shining these quite powerful lasers, you're in fact coming close to hitting the quantum limit. So for people who know the Heisenberg uncertainty principle, right, if you push on something, if you try to measure something very precisely, you end up changing a state by the act of making a measurement. So this is becoming a problem. You're pushing so hard with the laser photons on these big 40-kilogram masses that you're actually shaking them by pushing them with the photons. So all of this is creating a problem. There are some other problems that maybe people didn't quite anticipate, like this one here. This is actually a ranger. I'm not entirely sure, how good this ranger is at spotting things. If the ranger didn't spot this, rather large 4-kilometer long cement arm, but well, so be it. The result of all of this is that somehow it turned out that it was really possible to get the instrument sensitive enough. And on the 14th of September of 2015, the first gravitational wave that shook the world, GW150914, was picked up by this instrument. It was only about 0.2 seconds long. It came from a merger of two black holes that were each about 30 solar masses. And that's the one for which I suppose Barry, Ray, and Kip won their Nobel Prize. Since then, LIGO has picked up several more gravitational waves. There are now about 6 or 7 events in total that the LIGO collaboration has published. Of course, searches are ongoing, and the detector is getting more and more sensitive. So the rate of discovery should only pick up, and that means that we should expect that by the end of this decade, we may be having a gravitational wave every week or every day, or maybe even every few hours that's being announced by the LIGO collaboration. So that means it's time to do some science with them, and I won't talk about the astrophysics part of the science, but suffice it to say, remember that picture which has lots and lots of question marks on it, where I showed you sort of how the two stars might have evolved in order to come together, how they might have done some mass transfer, how they went through this funny phase I call the common envelope, and so on. I would really like to understand those question marks much better and remove those question marks. And the way to do that, in my view at least, is to use these gravitational wave detections as a tool. Think of a paleontologist, right? A paleontologist discovers a dinosaur, or doesn't discover a complete dinosaur, discovers, a few elements of the dinosaur skeleton, a jawbone here, a big toe there, and using her knowledge of anatomy and physiology, she can figure out from just these few skeletal remnants what the dinosaur looked like and how it behaved, what it ate, was it a herbivore, was it a carnivore, if it was a carnivore, did it hunt alone or together, and so on, just from those skeleton remnants. Okay, I want to do the same thing with the observations of gravitational waves, namely to say, okay, we've got these observations. They are basically the remnants, the skeletons of massive stars, the black holes or massive stars leave behind. Can we now, by looking at the properties of the population of these objects, figure out what got the stars there in the first place, what the stars must have been like when they were still young and alive and evolving? And that's, I think, one of the key challenges of gravitational wave astronomy. But to do that, we have to be able to infer the properties of any given merging binary in order to figure out the population of these binaries, right? So we need to figure out what are the masses of the black holes coming together, what are their spins, where are these things happening on the sky, and so on. And that turns out to be a very non-trivial inference problem. So let me say a few words about this inference problem now. So typically, the inference problem is something like the following. We have a data set which we assume is just a linear sum of a model, the true signal, and noise, because our detectors ultimately are inherently noisy. So D is my data, H is the waveform, which is a function, of course, all of them are functions of time. There's a data stream in time. LIGO is recording data at a frequency of something like 16 kilohertz. And H is also a function of the parameters. So theta here are the parameters of the signal, right? So theta are things like the two black hole masses and their spins, so how rapidly they're spinning and in what direction their spins are pointing, and where the source is located in the sky, and whether you're looking at this binary face on or edge on, and if you're looking at it at an angle, by what angle is it inclined. Maybe if the binary is eccentric, parameters describing its eccentricity. How far away is this binary? A couple of parameters maybe you don't care about because they don't have a lot of astrophysical meaning, but that are still part of the description of the signal, like when did this merger actually happen and what was the phase at the moment of merger. So all of these mean that you have, yes, please, Derek.
So wrapped up in the theta is kind of describing that particular system, if you will.
Indeed.
And so things like the distance away, do you know that or do you have to infer it?
You have to infer it.
You have to infer, so everything in theta has to be inferred. It's not something you can measure.
Absolutely.
Okay.
So there are some very special situations where you may know the information from in a different way. So for example, the location in the sky, okay, one of the 7 LIGO signals to date was a merger of 2 neutron stars rather than 2 black holes. And in that case, we were fortunate enough to be able to electromagnetically observe the merger as well, meaning telescopes could see that there was suddenly a transient, something that was very dark before and that went very bright for a while. Telescopes are really good at pointing, right? LIGO is actually not that great at pointing. Telescopes are fantastic at it, meaning that they are able to localize this very, very precisely. So in this case, for example, the 2 free parameters describing the location in the sky aren't free anymore. You can say, well, I know them from the telescope observations, right? And the telescope observations also give you some additional constraints and a couple of other parameters like the distance, although not perfect ones, right? So there are situations where maybe there's some auxiliary information you can put in, but most of the time, theta, which has, depending on how you count, 15 or 17 parameters, typically these are really the unknowns. These are the things you need to infer from the signal. The noise, the additive noise, is, of course, not something we can measure directly. If we did, we just remove it from the data and that's it. But it's something that we can try to measure the properties of. And I'll talk about measuring the properties of the noise later. But fundamentally, what you can say is, OK, maybe we make a very simple assumption, assume that we have stationary noise. So noise is essentially the same now as it was, OK, at least a few seconds or a few minutes ago. So I can look at some off-source data and figure out what is the power spectral density of my noise in an off-source moment, and then maybe I assume that my noise is Gaussian, so meaning that at least if I think of my noise in the frequency domain and I have the power spectral density, I just am drawing randomly the actual amplitude of the noise according to the measured power distribution, and that tells me the properties of the noise that allow me to try to do this inference, right? For the model, what I typically have are actual numerical models, or sometimes analytical approximations, as I'll discuss in a second, that tell me if I assume that it has some parameters theta, this is what the signal ought to look like. And now I'm trying to analyze a fairly large data stream. OK, what I mean by large? Well, let's say we're talking about data being recorded at 16 kilohertz. Now, sometimes we have 2 very massive things merging together, like for these very first events. We're only talking about a fraction of a second, so maybe it's only a few thousand data points. But as we look ahead into the future, we're going to be seeing, first of all, we're already seeing events like the double neutron star merger, where the duration of the event in the LIGO frequency sensitive band is a couple of minutes. So now we're already talking about approaching not a few thousand, but maybe a million data points. And as you look even further ahead into the future, detectors will become more sensitive at low frequencies, and potentially we're now talking about data sets that are hundreds of millions of data points long. In addition, we have to coherently analyze data from several detectors, because there's the detector, there are several detectors operating at the same time, and you really want to use all of the data together. We, of course, want to put in some a priori information. So we might, for example, have some astrophysical prior on the typical distribution of sources in the sky, or their typical masses. And so we want to infer, of course, the posterior distribution of the model parameters. We have to worry about the fact that the posteriors might be multimodal. So here's an example. This is not a real event. But this is what you get from a typical injection, where you see there are actually 2 different locations on the sky where the event could have happened. So the star represents the real event, and these 2 arcs are the result of our inference. Basically, the sky location is determined largely through triangulation. So if you know how your GPS works, right, you ask, OK, there are several satellites. They're all sending little beeps at me. Which one am I hearing first? That's the one that's closer. okay, if we play the same game with these gravitational wave observations, if you imagine that the gravitational wave source was somewhere over there, and Derek has one LIGO detector, the one in Louisiana, and I'm the other one, the one in Washington, and Derek detects a signal a few milliseconds before me, that means the signal is coming from somewhere, on that part of that side of the sky. If I detect the signal a few milliseconds before Derek, because the separation between us is about 3,000 kilometers, and you remember gravitational waves travel at the speed of light, so they go through this distance in about 10 milliseconds. If I see the source, 10 milliseconds earlier than Derek, that means it's coming from that direction. But of course, if let's say we both see it in the same time, it just means it's coming from some great arc like this. And now with two detectors, it's very difficult to tell exactly where in the great arc the source happens to lie. So that's why you're seeing some of these degeneracies. And okay, of course, let me say, already a couple more words about the model and the data. I think I've already mentioned a few things, but the first one is the data actually are publicly available. So for anybody who wants to play with the data, here is a website. This is a website run by the LIGO collaboration. By the way, I should say I used to be a member. I've since left the collaboration, but I still, of course, use their data, which they make public for any event that they have detected. So you can download the data and play with it. The data, as described here, they've been slightly downsampled. So they're sampled at about 4 kilohertz on this website. The data streams can be less than a second and perhaps hundreds of seconds long, but can get longer. I'll mention more about how they get longer in the future, how they will get longer in the future in a few minutes. So I already told you that H is this waveform model, which is typically based on numerically solving Einstein's equations, right? So Einstein's equations are the equations describing general relativity. They are quite convoluted, coupled partial differential equations. And that means that except in some very, very special circumstances, there are no known analytical solutions. Okay, there are analytical solutions known for a single, completely static object. That's called a Schwarzschild black hole, non-rotating black hole. There's a known solution for a rotating black hole, a stationary solution that's known as the Kerr black hole, and that's more or less it as far as astrophysically relevant solutions go. So if you want to solve this problem for two black holes orbiting around each other, you have a couple of options. You can either do perturbative expansions relative to some regime where you can kind of roughly approximate what the solution is going to be like, or you have to solve them numerically. Solving them numerically turns out to be very, very challenging because the system is so strongly nonlinear that you end up, when you try to solve this numerically, you end up having runaway modes that are very difficult to suppress. Now, I'm probably not the right person to discuss this in detail, but if you want to chat about this later, we can. But fundamentally, it's taken something like 40 years to be able to get to the point where these equations could actually be solved numerically. After 40 years of trying, Franz Pretorius had a breakthrough in 2005, and now there are some numerical solutions, but typically it turns out the numerical solutions aren't actually long enough to describe the entire in-spiral and merger of two neutron stars, for example, because they're just too computationally expensive. You only do this for a few orbits, so often you end up stitching together an analytical solution and a numerical solution, not to mention the fact that the numerical solution is very computationally expensive. So it might take, if you want to figure out what this h of theta is for a particular set of parameters theta, you might need a few months on a cluster to solve this numerically, right? And if you want to explore a broad parameter space of theta, that quickly becomes intractable. That's one of the challenges. As a result, there are some waveform implementations, typically some approximations, as I'll describe in a little bit more detail below, and some of them are again publicly available if you don't want to implement waveforms yourself. There is a public, LIGO provides all of their software in public, so you can download the waveform implementation. The computational cost varies a lot. Some of them are essentially analytical, so you can compute a very long waveform in a small fraction of a millisecond. Others, even the ones in here, they're not doing full-blown solutions of Einstein's equations, of course, full-blown numerical relativity. They're doing some approximations, but even some of the approximations are computationally challenging. So you might be talking about, let's say, a minute to compute a single relatively long waveform. And finally, as I mentioned, the noise is typically assumed to be stationary and Gaussian, but of course doesn't, with a power spectrum density that's empirically measured during some off-source time, but that does not need to be the case. Okay, so with that bit of intro, okay, I don't think I need to explain this to this audience, right? The obvious solution is you do Bayesian analysis, and you try to stochastically explore this large dimensional parameter space, and that's something that, of course, we've been working on in this gravitational wave data analysis community for now more than a decade. You can see some of the papers on this listed below. The basic idea is, of course, okay, we want to figure out the posterior probability density function on the parameters theta, given the data, and given our gravitational wave model. So we write down Bayes' theorem, we put in some priors, we say the likelihood is proportional to, well, if you assume the noise is really stationary and Gaussian, then all what we really need to do is we need to subtract the data from our model, figure out the residuals, and then minimize, if you wish, the noise-weighted sum of the squares of the residuals, right? Okay, we don't want to just minimize it. We want to figure out what is the, not just what the maximum a posteriori parameters are, but what is the uncertainty on those parameters. So, of course, we consider the probability that these particular parameters could be responsible for the signal. And we end up with something that behaves like this, right? So this is, okay, this is a two-dimensional representation of our Markov chain Monte Carlo search. So here are the two masses, M1 and M2. Our chains are happily running along. Of course, they're running along also in 13 other parameters, which I'm not playing here, and the process is a little bit slower than it's shown. This is being quite a bit sped up, but you can see that towards the end of this, you're finding this sort of banana-shaped distribution, for example, for the two masses, and that's a real degeneracy. It turns out there's one particular combination of masses that is easy to measure and one that's difficult to measure. Did you have a question?
Can you just explain which priors you use for these simulations?
Sure. So the priors, of course, are different for different parameters. So, for example, for the masses here, I think we've actually chosen very simple priors. So uniform priors on the two masses, flat between a solar mass and 100 solar masses or something like that. For the sky location, the uniform in the sky, and uniform in volume, meaning the prior on distance goes as distance squared is proportional to distance squared. For the inclination angle, again, a uniform angle, etc. So, and these are perfectly reasonable choices here. Of course, the hope is that if you have a sufficiently strong signal, then the priors don't matter too much, but you also want to give yourself the freedom of correcting for them at least after the fact, right? So if I, for example, say, okay, but you have measured all of these properties, but assuming that, let's say, the spins of the two black holes are completely randomly oriented relative to the binary, but I have my favorite astrophysical model, which says that the spins are going to be perfectly aligned because of the mass transfer that happened during the evolution. I want to be able to check, okay, first of all, do I get substantially different masses, for example, if I do that, but also, are my data in fact consistent with this model that says that all of the spins are perfectly aligned? So I may want to reanalyze the data or do some resampling after the fact or whatever. Okay, a couple of words on computational cost. So of course, okay, if we're doing something like, let's say, a Markov chain Monte Carlo, the computational cost is obviously just the product of the number of likelihood evaluations times the cost of each likelihood evaluation. And so there are a couple of things we can try to change here. We can try to change the number of evaluations, or we change the cost of each one. If you want to decrease the number of likelihood evaluations, okay, there are a few things we have tried, and maybe there are more things that you can recommend. But so we've tried, for example, doing parallel tempering within our Markov chain in Monte Carlo, some kind of annealing, adaptive step sizing, differential evolution, nested sampling, including multi-nest, genetic algorithms, ensemble samplers, and so on, all as tools for trying to speed up the process, make it more efficient. And then some problem-specific tools. So for example, smart jump proposals, where we know, instead of using some black box, we can say, look, actually, I happen to know that because of the physics of my problem, there is going to be a particular degeneracy. For example, if I have 3 detectors in a plane, it turns out that there's a degeneracy or near degeneracy in terms of the reflection symmetry through the plane, right? So instead of relying on my sampler to stochastically allow me to get to the other solution, I might just say, okay, once in a while, I'm going to propose a jump which is just a reflection symmetry across the detector plane, and see if that also gives me a high likelihood, right? So these are the sorts of things we can do to try to step away from completely stochastic sampling. So in the interest of time, I'm not going to go through this in any detail, because I think you guys know much more about many of these tools than we do. We've kind of figured out a few things. So for example, I think we figured out a reasonably good way to, as far as I know, it might be the sort of a relatively new thing, figure out how to automatically adjust the temperature ladder when doing parallel tempering, so that you don't get any bottlenecks and you actually have information propagating properly between the different temperatures, between the chains at different temperatures. How to do some work on, let's say, interpolation if you're going to do jump proposals, for example, when doing reversible jump MCMC. A few things related to the idea that maybe sometimes you don't even want to do stochastic sampling. Of course, stochastic sampling works great if you have a lot of dimensions. If you have fewer dimensions, then maybe moving away from stochastic sampling is actually not such a bad idea. And so there are some ways which you can do to, some things you can do to show that in fewer dimensions, you might in fact be better off by doing a very cleverly chosen grid instead of doing stochastic sampling. But other methods, by the way, that people have worked on include just faster likelihood evaluations. So for instance, being able to compute waveforms faster, reduce order modeling, reduce order quadrature. Another possibility might be to interpolate the likelihoods. So it's challenging to build emulators for the models, but you can do it to some level, for example, with reduced order modeling. But you can also try to build an emulator for the likelihoods themselves. The idea there is, okay, likelihood is a single number as opposed to a long and difficult model. And if it's smooth enough, then maybe you can build an efficient interpolator there or an emulator there. And we've had some success with this. So in principle, this is doable, but clearly challenges remain. Now, just to show you that we actually can do this, right? So here are the results for GW150914, this very first binary black hole that has been detected. So here are the posteriors in mass space. Of course, these are the two masses. These are the projections, marginalized projections onto the individual masses, M1 and M2. You see, of course, we don't measure the masses perfectly, but okay, we know, for example, these are really 30 solar mass black holes and not 1.4 solar mass neutron stars with a lot of confidence. So far so good. We know also that we can get results for, let's say, the location in the sky. In this case, it's a big blob. In the double neutron star case, it turns out we could measure the sky location much better, and that's why people were able to point their telescopes and detect the electromagnetic counterpart. So that was very exciting and very useful. You can also see that we have a couple of different approximants here, right? So these are different waveform models, right? Remember I said that we don't know the waveforms perfectly. We only know them up to some best guess, some approximation, because even when people solve the equations purely numerically, there are some numerical errors. And if you're going to stitch those numerical results onto some analytical models that describe, for example, what the waveform looks like in the early stages when the binary is still pretty far away and moving relatively slowly. It turns out there you can do a perturbative expansion. that stitching introduces some errors, and if you then want to do some build some emulator to allow you to compute these things much faster over a broad parameter space, okay, that emulator introduces some errors. And so here there are a couple of waveform families, right? So think of them as two different kinds of emulators, if you wish. And one of the reasons we're trying both is to see, okay, is there we don't know what the ground truth is, but at least we can tell, okay, if these things agree with each other, that's telling us that probably we're not so sensitive to systematic errors in the waveform models. If, for example, we got two very different blobs, a blob here and a blob here, we would know that we're really limited by our systematics rather than by the statistical measurement uncertainty. So here, the answer is that, at least in this particular case, we're in fact limited by the statistical measurement uncertainty, not by the systematics. But that can change, because as you get louder and louder signals, higher and higher signal-to-noise ratios, which will happen as you get more sensitive detectors, that is going to, what it's going to do is it will decrease the statistical measurement uncertainty, which, roughly speaking, scales inversely with the signal-to-noise ratio, but it's going to leave the systematic bias between two different models the same. So unless we either manage to get better models or figure out how to also marginalize over the uncertainty in the models, we're going to have a problem where we'll have, at some point, one blob, a very small blob here from one of these models and another blob here from another model, and they won't be on top of each other, and we won't know what to do. Okay, I'm going to skip a couple of these. Okay, you can also measure some parameters related to the spins and related to the orientation of the spins and so on. These are not particularly well measured at present, but you can see this is the kind of game we end up with in the end, is that we measure a lot of the parameters of the system, of course, all with some suitably described uncertainty. Okay, so far so good. Our different models seem to agree with each other. We could also actually say, okay, what if our model of GR is completely wrong, and introduce some extra parameters that describe the deviation from GR. And what those parameters, so far, what it tells us is that really all of these parameters, their posteriors are consistent with 0, which is basically telling us that as far as we know, general relativity is really the correct theory of gravity. We see no evidence for deviations away from general relativity. The graviton really is massless, and it's really moving at the same speed as the photons move at the speed of light, and so on. So what are the remaining challenges? Well, one of them that I alluded to earlier is that the computational cost is going to increase. The duration of the waveform from a given frequency until merger scales as that frequency to the minus 8/3 power. That means if you improve the detectors to have better sensitivity at low frequencies, so right now the low frequency wall is at around 30 hertz. If, let's say, you bring it down to 3 hertz, bring it down by a factor of 10, that means your signals are spending something like a factor of 500 longer in the sensitive band. So you just have 500 times more data to deal with. The waveforms take longer to compute. The likelihoods take longer to compute. Okay, you have a problem. The second issue is noise characterization. Is the noise really stationary? Is it really Gaussian? No. And how do we deal with that? Waveform systematics, I already mentioned. We know we don't have the perfect model. And okay, potentially a little bit more in searches for alternatives to general relativity as the correct model describing gravitational waves. So the computational cost of future detectors. So one of the things you can try to do, and this is what we've done so far, is to implement multi-banding. So the idea is that, look, of course, if you go to lower frequencies, you do have greater and greater signal duration in band, but also at those low frequencies, you're really talking about being, well, in a low frequency regime, meaning you don't need to sample the signal at the same high frequency. You could actually just choose to downsample your signal if you're working, let's say, in the frequency domain to do these calculations, right? And that means you only need to sample at with a high sampling rate. Okay, you know about Nyquist frequencies, right? You need to sample at least twice the frequency of whatever components of the signal you might think are in the data, you only need to do that during the very short, relatively short time period when your signal is at high frequency. So that turns out to win you back another factor of f. So you go from this f to the minus 8/3 problem, which is what you would get naively, to something that looks more like f to the minus 5/3. That would be the green line. Okay, our actual data is in blue here from our implementation. It's a little bit imperfect. You can see it doesn't quite go down as the green line does, but it does better certainly than the red line, and we can probably make this a bit better. That's just a technical issue. But that only gives you back one factor of f, so that's clearly not the full solution. Secondly, noise. Okay, this is a spectrogram during one of these binary mergers, an actual spectrogram of the data, normalized by the noise power spectral density. This thing you see here, so moving up, so this is time on the horizontal axis, frequency on the vertical axis. So as time goes on, the frequency is increasing in this characteristic line. Okay, that's your chirp. That's the gravitational wave signal. That's the thing that goes, right? That was a chirp. This is not a chirp. This has nothing to do with gravitational waves. This big, giant yellow thing, that's something went funny in the detector, okay? Something, there was a little power surge, and one of the mirrors suddenly shook. There was a train that happened to go by, and it shook the suspension system. All kinds of things can go wrong. Somebody opened the microwave in a building a couple of kilometers away at the wrong moment, right? These things are incredibly sensitive, right? So look, this is not stationary and this is not Gaussian, right? So we have to somehow deal with this. And again, there have been attempts to deal with this. So for example, there have been attempts to say, okay, well, look, in addition to this stationary Gaussian noise and the gravitational wave signal, let's also assume there is some other noise which, let's say, we can describe by some wavelet representation, a bunch of signed Gaussians or something like that. So we allow actually a tripartite mixture, gravitational wave signal, stationary Gaussian noise, and some non-stationary noise represented in a suitable way. And then maybe we can actually subtract this extra noise like this. And it turns out that indeed you can with this glitch model. And you can, because the glitch model is sufficiently different from the signal model, you can largely remove it and continue on with the data analysis. But this is still very much a work in progress. What if we don't have the perfect model? Okay, so here I was just trying to play around for the purpose of this talk with checking, okay, what if I have some systematic bias? So I took a couple of different models here and said, okay, how the color basically is how good my match is between the data and the model, where I actually assume that there is no noise, there's a zero noise realization in the data. So red means excellent, blue means okay, we know that this is not the right model, the parameters are wrong. Here are the two parameters. It's a slightly reparameterized mass, but basically these are two parameters that describe the mass. The x here represents the injection parameters, and the pink diamond represents the best fit parameters. And you can see that the best fit parameters lie exactly on the injection parameters when I use the same model for the mock injection and the analysis, the inference. Here I use a different model, and lo and behold, you can see that I'm basically going to convince myself that the true parameters ruled out and the actual parameters are sitting somewhere over here, right? Okay, now here I took a slightly extreme version. It was a very loud event that I simulated, and let's say my two waveforms models are probably different by more than the real uncertainty in the waveform models that we have right now, given all the improvements over the last decade in the waveform modeling. So this is, don't worry, it's not really this bad, but it can be a genuine issue. And so again, there has been some work done actually by people here at Cambridge. Well, at least at that time they were in Cambridge, Chris Moore and John Gare, who thought about, for example, maybe we could use Gaussian process regression as a way to deal with the uncertainty in the models themselves by saying that, yes, we don't know the models perfectly, but maybe there are a few points in parameter space where we do know the models very well, because that's, for example, where we have very accurate numerical simulations. And then if we have some emulator model, we essentially describe the difference between the emulator model and the ground truth using some kind of a Gaussian process, and that allows us to then marginalize over the properties of the Gaussian process. So in the end, of course, that means that we have a less accurate measurement, less precise measurement, let's say, but at least it doesn't suffer from wild inaccuracy because we've convinced ourselves we know the model perfectly, and now we place this magenta diamond in completely the wrong place, right? There are still some challenges, of course, associated with trying to figure out the best way to parameterize alternatives to a GR model. So what should we do? Let's say we have some true signal, within the GR model. So this black line represents kind of the manifold of all allowed signals under the general relativity model. Now we measure something over here. So we measure this red point. It's off of this manifold. Does it mean that GR is wrong? Or does it mean that we just had a bit of noise that lifted us off the manifold? Well, the answer is we typically don't know. We can just look at this distance and say, is this distance consistent with noise? So that's one of the ways to try to constrain whether general relativity is correct. But maybe we can do better. Maybe we can choose to parameterize deviation in some sensible way like we do here. Maybe we can do some model selection between two alternative theories of gravity. There have been some attempts to do this. I think I can still do better by finding improved parameterizations that are more sensitive to deviations from general relativity. So, okay, I am conscious of the fact that I was asked to leave 10 minutes for time. So let me just bring up this nice slide here, because I think this tells you once XKCD gets onto something, you know that you've really made the mainstream. So in this case, XKCD has really gotten onto this. Gravitational wave detectors work, and we can now listen to the signals carried by ripples in the fabric of space itself. So we can get all kinds of cool events, like a black hole merger, or the fact that Zorix and Mighty would like to connect on LinkedIn, or maybe a mortgage offer in the Triangulum Galaxy. Either way, there is hope for a lot of things to learn from these gravitational wave detections, and hopefully some of you will have some ideas for how we can learn even more and do even better. And I'm done. I'm just going to run this little animation if I may succeed. Well, maybe I won't succeed. Okay, that did not seem to succeed. Oh, look, there it is. Perfect. Anyway, that was actually the end. Thank you. That's a numerical simulation showing the evolution of the two black holes.
All right, questions?
Thank you. Did you try to do kind of sensitivity analysis to understand which parameters make strongest impact on the result?
Absolutely. So even before, of course, we had any detections, the simplest thing that people have started doing 20 years ago to figure out how well we can measure parameters were Fisher information matrix type analyses, right, where you just say, okay, if we have some data, how well do we expect to be able to measure the parameters, and therefore which parameters change the model the most, right? So you basically compute a kind of gradient of your waveform of your signal as a function of the parameters. Of course, you've seen this, as an example when we looked at the mass distribution, the posterior and the mass, and you saw this sort of banana shape, right? So the banana shape basically meant that there were two particular mass combinations. You can reparameterize this as a kind of, parameter that goes along the banana, which turns out to be the mass ratio, and a parameter that goes perpendicular to the banana, which turns out to be a particular mass combination. And you can say, look, this is a mass combination that's measured very well. This one is measured poorly. And that's very useful, for example, for proposing jumps, right? So if you want to propose jumps while doing a Markov chain Monte Carlo or nested sampling or something of that sort, it turns out that it's actually a good idea to use jump proposals in the parameters which are relatively orthogonal, so doing a kind of sensitivity analysis allows you to do that.
Yes, I'm sorry. Okay. Well, Michael, go first. I'll get you next, Henry.
Hi. Okay, so in your basic equation, you have a delta noise which is just a function of t, not of theta.
Yes.
I mean, is that because it really is, or because it simplifies the calculations?
So we think it really is. So we think that the noise in this case is genuinely just something that happens in the detectors, and it's added. There's no sort of coupling between detector noise and the signal itself, right? So the noise is coming from photons hitting the mirror surface and making the mirror surface vibrate in a kind of Brownian motion. It's not really connected in any way to gravitational waves. So I think that part is probably true. There is the one sort of noise component you might imagine, if you want to think of it as noise, is the systematic noise, right, where you have noise in the model. Your model is uncertain, and that uncertainty could very well be a function of the parameters, because, for instance, if you're using an emulator of some sort, right near where you did a laborious 3-month calculation in a supercomputer, the noise is small, and far away from that, the noise is much larger, the uncertainty is much larger.
So the only thing I ask is, usually people, I thought you'd say something like the L, like 10% or something. So the stronger the signal, the less it would kind of, the chance that you actually miss it. So that you would normally imagine, to me, I would imagine if the signal was very faint, there would be more, it would be harder to detect it, rather than if it's strong, and the amount that I would weaken. You say it just doesn't happen like that?
No, you're absolutely right that the detection, so there is a signal-to-noise ratio, right, that you can compute, and the threshold for detection is at around a signal-to-noise ratio of 8 or 10 or so. So, of course, if the signal is weaker than that, you just don't detect it, then there's no reason to even discuss this inference, right? But if it's stronger than that, then you have a detection. The question is, how accurately can you measure the parameters? And typically, okay, at least in the very high signal-to-noise ratio limit, you can convince yourself of this just by doing a Fisher-Matrix calculation, that you're sort of in this linear signal approximation limit. Your uncertainty on an individual parameter is going to scale as 1 over the signal-to-noise ratio within this additive noise model.
Henrik, you mentioned that some people use singular perturbation of approximation asymptotic theory, and you also mentioned the fact that you had the different models at different wavelengths. So you've got some sort of hierarchy of models at which at some point you're using the approximations, at some point you have a huge simulator which you emulate. I wasn't quite sure what scale you were doing using which models.
So that's exactly right. So when you're, the simplest models, the very computationally efficient ones, the ones which are essentially analytical, are so-called post-Newtonian expansions. They're basically expansions in powers of v over c, where v is the orbital velocity and c is the speed of light. So if your binary is far enough apart, it's moving slowly. It turns out that a simple perturbative expansion does a pretty good job of explaining this, but it breaks down completely by the time that the binary is close to merger and moving at half the speed of light. So there, you really need a full numerical solution. Then you try to attach one to the other, and then you can have different levels of sophistication in how you do the attachment and how you try to build emulators for that attachment over the parameter space theta, over the different masses and spins and so on. And some of those emulators are thought to be maybe a little bit more accurate, but suffer from being much more computationally expensive. So that gives you a certain hierarchy of accuracy. There are, of course, the direct numerical simulations. We typically can do a few of them in the relevant portion of the parameter space, but you cannot, if you're trying to do Markov chain Monte Carlo and you are trying to draw 1 million samples, it's completely implausible to actually do the full-blown numerical simulation 1 million times for 1 million different parameter choices. So
just a quick follow-up. So the prior distributions you put on these parameters, do they kind of change according to the level of fidelity, complexity of your model? Like the simpler models, you know better how to choose a prior distribution.
No. The priors really come in this case from our astrophysical assumptions about, for example, what we think is from other observations, what we think is the distribution of the masses of black holes in the universe, and are independent of the details of the models used for simulating the general relativity signal.
Peter, then,
So you said that the models were very hard to emulate, so you emulated likelihoods instead. What is it about the models that makes them so hard to emulate?
Well, so they're not. So people have tried to emulate the models themselves as well, right? So likelihood was just one possibility, maybe, to see if it would work. I mean, in general, no. I mean, all of these reduced order modeling methods, reduced order quadrature, etc. They're precisely attempts to emulate the models. I mean, the challenge is that, of course, you are talking about emulating something with multiple cycles, sometimes multiple hundreds of cycles with changing amplitude, changing frequency, and these are large dimensional parameter spaces, right? And that's fundamentally what makes it a challenge to come up with a reasonable and robust way of doing the emulation. But no, in principle, this is people have been trying to do this. It's just a question of how far they've gotten.
They're very normal smooth or something.
No, they're fairly smooth, but I mean, actually, you can really think of this as sort of a at lowest order as a kind of a sinusoidal with ever increasing amplitude and frequency. But then you say, oh wait, but if there's spin and there's precession, then you also have a changing envelope to the amplitude, and as you keep on adding more parameters, you find that things get increasingly more complicated.
I wanted to go back to your list of question marks, and I wondered if you could say a little bit more about how the way you've characterized the inference problem will help you answer those question marks.
Oh, I see. You mean sorry, the question marks. You mean pardon me. These ones.
Yeah, because it seems like you're almost in 7 when you're doing the inference problem. But I wondered where the question marks come in.
Okay, so that's in principle that's a whole separate talk, and I would love to give the talk. But the short answer is the following. So, for example, you can see things like, you don't get it from a single observation. What you get it from is the distribution of the observations and the distribution of their properties. So, for example, if you see that, very naively, if you see that all of your black holes and binary mergers have very low masses, and yet you know that there are plenty of high mass stars, that's telling you that at some point in their evolution, the stars must lose a lot of their mass to make lower mass black holes. So that's telling you something about the supernova explosions and the wind mass loss, right? If you see that, for instance, all of your black holes have really almost identical masses, there is never a significant mass ratio, that's telling you something about the stability of the mass transfer in unequal mass systems. So it's telling you something about what happens when one object starts to transfer mass onto the other one. If you look at how the rate of mergers changes as a function of distance, as a function of what's called redshift in cosmology, we know what the star formation rate was at different epochs of the universe. And so if the observed rate of mergers completely tracks that, we know the typical delay times between formation and merger are short. If, on the other hand, it doesn't track that, that's telling us that there's a very long delay time typically between formation and merger, meaning all of these things will still happen in a couple of million years because massive stars evolve very quickly. It means that this process is taking much longer, which means that when the two black holes form, they still form quite far apart and therefore take billions of years to merge through gravitational wave emission. So these are the sorts of things we can use to try to understand the answer to this problem. But yes, we can talk more about this. As I said, that's a whole separate talk.
I'm going to, just to finish things off, I'm going to ask a couple of questions, if that's okay. All right, so you have a particular type of inverse problem. You've got a model that you don't want to evaluate over and over and over. And you've got data. And in some sense, what you want to be able to do is make inference about the parameters that govern the system you're looking at based on that data. Is that correct?
Yes,
yeah.
absolutely.
So you've got noisy data, you've got model, and you want to put those two guys together.
Absolutely.
Right? And you can't evaluate the model millions of times, the H, if you will.
Yes, ideally, or at least not the most precise model. You can evaluate some approximate models millions of times.
You can have a hierarchy of models, but the supermodel,
Yes.
you can't. Okay, so that's one thing about your setup.
Mm-hmm.
So I'm going to have two questions before we run to coffee. One of them will be, because I think some of the mathematicians in particular will want to know if you could tell them something about the form of H, because that often informs the sort of problem that the sort of solution that you might start making some headway on. And the other one being, it's a bit broader question, All right, so if everybody in this room lined up to say, I'm going to solve a problem for you, what would those problems be? Because it seems that you guys, seems like you're actually interested in enlisting, if you will, some of the machinery that people here put together and do research on. What can people do for you? So that'll be the second one.
Okay, I mean, the answer to the first question, so maybe I should actually check that I understood the question properly, right? So when you say what is the form of H, right? Okay, I mean, literally H is an array of values, right? As a, given the parameters theta, you have a, okay, there's not to be a complex array of values, but in any case, you have, there are two phases to H, but you have, let's say, the real part of H which as a function of time, and the complex part of H as a function of time, right? In terms of the mathematical solution, okay, in free space, H is just a wave, literally, so it's a solution to the wave equation. The D'Alembert of H is 0. Of course, there is a source term here, and the devil is, of course, in correctly describing the source term, because the only way to correctly describe the source term is to solve Einstein's equations. G mu nu is 8 pi T mu nu, and where T mu nu is the stress energy tensor that's sourcing the Einstein tensor, and this is the part where it's taken 40 years to even figure out how to evolve a single orbit numerically. So as far as the second question goes, I think that the key challenges from my point of view are, one, how to deal with systematic model uncertainty. Two, what can we do as we're preparing for future generations of detectors? So I sit, for example, on the science team of something called the third generation detector. LIGO is sort of entering its second generation phase, so third generation detectors would be things you put underground. It might be another 20 years before they're built, but if they are, they will have sensitivity not from a few hertz, but probably from 1 hertz upwards, which means we're really talking about a binary star being in band for a week. These will be fantastic signals, very loud, very strong, lots of information, and we might really be hitting a wall in terms of now not the detector quality, but being able to do inference on these signals, because the data streams are just going to be too large and too complex using our current methods. So what could we do better as we move towards longer and longer signals? And maybe another question is, are there, and this is related to the previous one, are there better things we could do to build emulators, or maybe, as Derek described, sequences of ever more precise emulators, either for the waveforms themselves, or for the likelihoods, or for something else relevant to our problem, so that we can actually try to make this computationally tractable going forward.
Okay. All right. Well, thanks for that.
Thank you.
Let's thank Ilya again.